Welcome back, everybody. In this section, 6.4, we'll be looking at what's called the central limit theorem. The central limit theorem gives us some guidance about the sampling distribution of the sample mean. And so the theorem reads like this. For all samples of the same size n, where n is bigger than 30, the sampling distribution of the sample mean can be approximated by a normal distribution with a mean of mu and a standard deviation of sigma over the square root of n, where n is the sample size. So basically this tells us how, or will tell us how the distribution of the sample mean will look. As an example of calculating the standard deviation, and then we'll do a fuller example after this, let's take a look at the following example. Here it says overhead reach distances for women are normally distributed with a mean of 205.5 centimeters and a standard deviation of 8.6 centimeters. We want to find the standard deviation first for a sample of 25 women. So overhead reach distances, let's say you're getting on an airplane, you're trying to put your luggage in overhead compartment, or maybe you're sitting at a desk and trying to reach a shelf over your desk. That's your overhead reach distance. For women, we're told what the mean and standard deviation are, and we want to know for a group of 25 women first what the standard deviation for that group would be. And so it's going to be sigma over the square root of n. Here our sigma is 8.6 centimeters, and we're going to divide by the square root of 25. And so that's going to be 1.72 centimeters. So that tells us how variable, not what an individual woman's reach distance would be, but if we were to take groups of 25 women and calculate the mean of those 25 women, how variable all those means would be. If we take a group of 40 women, it will still be sigma over the square root of n, but it'll be 8.6 over now the square root of 40. So let's calculate that. That's 1.36 about. And that's still in centimeters. And then let's lastly do that for a group of 9 women. So again, that will be 8.6 over 3. And that's about 2.87 centimeters again. All right, so again, what it is that we're calculating is basically how variable the mean is if we take groups of women of a certain size. If you take groups of 9 women, if you think about it, if you have a group of 9 women, the mean is going to be relatively more variable than if you take a group of 25 women. And if you take a group of 40 women, that's an even bigger group, it's going to be even less variable. So the bigger the group size is, the less variable the means will be, is basically what this is saying. In short, you're going to take the standard deviation and divide by the square root of the sample size. And if you think about how fractions work, if you make a denominator of a fraction bigger by making the sample size bigger, that's going to make the fraction smaller overall. Okay, so more on the central limit theorem. Suppose that we're given a population that has any distribution, could be normal or not, but it has a mean of mu and a standard deviation of sigma. And we're taking, as always, simple random samples, the same size samples all the way through. We can't take 25 women in one sample and then 27 in another. For example, we have to have all the same sample size throughout. So what do you get? if either the population has a normal distribution or the sample size is bigger than 30, the mean of the sample means is going to equal the population mean. And the standard deviation of the sample means is going to be the population standard deviation divided by the square root of the sample size, as we saw before. That standard deviation of the sample means is denoted by sigma and then a little subscript x bar. So sigma x bar is sigma over the square root of n. It's the population standard deviation divided by the square root of the sample size. Okay. So more fine print, and then we'll get to some examples. In order to use the central limit theorem, we need to have either the original population being normally distributed or the sample size being bigger than 30. If you don't get either of those two things, then you will need to do something else that we haven't covered yet. So for now, the populations will be normally distributed or the sample size will be bigger than 30. If you don't get those things, we'll have to do something else, which we haven't seen yet. Okay. So in order to get started to do problems, we need to check and make sure that our requirements are satisfied. We need to either have that the original population has a normal distribution or the sample size is bigger than 30. You also have to check and see, is the problem asking you about an individual value, the overhead reach for one woman, for example, or is it for a sample, a group of some size? Decide if you're using a normal distribution with a single value x or the mean x bar from a sample of n values. If it's an individual value, use the methods we learned in section 6.2 and the x minus mu over sigma formula, if it's an individual value. If the question is about a sample of values, a sample of n individuals, use sigma over the square root of n for the standard deviation, so that for your z-score formula, it will be x bar minus mu over sigma over the square root of n. So pay attention to the way the problem's worded, what's being discussed to help you decide whether the central limit theorem should be used or not. So this slide repeats the central limit theorem kind of for your reference. I'll leave that in the notes for you to take a look at. And here's the formulas really that we want to be able to use. So let's basically try. So here it says the mean height of men in the US age 20 to 29 is 69.2 inches. And we assume that we somehow know the population standard deviation is 2.9 inches. Let's say that we'd like to know the probability that randomly selected 23-year-old men will be taller than 70 inches. So this question is about a single 23-year-old man. So that means that it's more like a earlier in chapter 6 question. We have a mean of 69.2 inches. And we wanted to know the probability that someone will be taller than 70 inches. So we will turn our 70 inches into a z-score. And for this, we're having just a single variable, a single individual. And so when we're dividing by the standard deviation, there won't be that square root of n underneath that we would have had if it were a group. So we get a z-score of, looks like 0.28. So let's look in our table for that. So 0.6103. That's our probability that z will be less than 2.28. We wanted the right tail though. So we'll take the complement of that. And so get 0.3897. That will be the probability that we'll get one 23-year-old man having a height that is greater than 70 inches. Now, let's say that we want to know the probability that if we get a sample of 30 men, that the mean of that 30 men will be greater than 70 inches. So our picture here will be very similar, so I'm not going to repeat that. What will be different is our z-score. Z will be mean of the sample means minus, sorry, let me restate that. That will be our sample mean minus the mean of the sample means divided by the standard deviation. Okay, so 70, our proposed sample mean, minus the population mean divided by that standard deviation. This time we will be dividing by the square root of that sample size, since we're talking about a sample of individuals, not just one individual. So let's calculate that. Okay, get 1.51. So as we're going through the calculations here, take a minute and think about whether you think the answer should be more or less than our previous answer. So we end up with 0.0655. If you think about it, this should make sense. We're told that the mean is 69.2 inches, which, okay, that's a measure of kind of what the typical height is. We saw the probability of having an individual having a height that is more than 70 inches is about 39%. If we're asking a group of 30 men to have a height that far from the average, it should be less likely to happen than having an individual deviate from the mean by a certain amount. We'll make the same calculation for a group of 60 men. Before we do that, take a minute and think about whether our answer should be more or less than for the group of 30. All right, so for the group of 60 men, I've completed the calculation, and then the only difference here is that I changed the n to 60 in comparison to the prior calculation where it was a 30 to reflect the doubling of our sample size. And then we end up with a z-score of 2.14, and then the probability of z being less than 2.14 of about 98%. And so the right tail is about 0.01. So the probability of getting a group of 60 men with a mean height more than 70 inches is just a little over 1.5%. As you can see, it's much less likely than when we had the probability of an individual exceeding a certain height. Okay, here's another example to try. For this one, we're told that credit card balances are normally distributed with a mean of $2,870 and a standard deviation of $900. We want to know, first of all, the probability that a randomly selected individual has a balance under 2,500, and then we'll see if we collect 25 cardholders, what would be the probability that their mean balance is less than $2,500. So let's go ahead and work through the details. For A, we're just doing this about an individual. So as always, though, it's going to be a good idea to make a little sketch. We're told that the mean is 2,870. We want to be less than 2,500. So that will be the left tail. So z-score. Z will be x minus mu over sigma. It's the simpler version of the formula because we're only talking about an individual this time. So we want to know our individual 2,500 in comparison to the mean of 2,870. That's divided by the standard deviation, which was 900. So let's go ahead and grab our z-score from that. That's negative 0.41. And that works out to be 0.3409. Okay, that's a probability on the individual. Okay, so now for the second part, we're doing this for 25 cardholders. Our picture is going to be the same, so I'm not going to redraw that. We're interested in comparing the mean of the sample, that is that 25 cardholders, against the mean of the sample means. That is, we're looking at all the possible 25-person subsets and calculating those means. We want to compare our 2,500 against that and determine what the corresponding probability is. So standard deviation was 900. Just write up in general first. That's sigma over the square root of n. For our specific case, we wanted 2,500, our mean of our sample, compared to the population mean. And our standard deviation is 900. Our sample size is 25. So as I'm calculating this, again, we want to think about what that probability is going to end up being. Will it end up being more or less? Be careful when you type all this stuff into your calculator. You get negative 2.06. So negative 2.06. 0.0197. So the probability is a lot less. Dropped down from 34% chance to just under a 2% chance. Because we're talking about the mean of a group rather than an individual. One more example. All right, so here, this one from our book. Here it says a brake pad manufacturer claims that its brake pads will last for 38,000 miles. Suppose that a consumer protection agency wishes to test the manufacturer's claim and randomly selects 50 brake pads. In the agency's tests, the mean life of the brake pads is 37,650 miles. Assume the lifespans of the brake pads are normally distributed and have standard deviation of 1,000 miles. In part A, it says, assuming the manufacturer's claim is correct, we want to find the probability that the mean of the sample is 37,650 or less. And then we'll go from there. All right. So let's see. Picture first. We're told that the claim of the manufacturer is that their mean is 38,000 miles. Okay. Sorry, that's upside down, backwards. Better? Okay. So the claim is that the pads will last for 38,000 miles. And we've gotten a sample that is 37,650. And it's possible that the manufacturer's claim is true, or maybe it isn't true. It could be that the manufacturer's claim is true and we just happen to have, by chance, gotten a sample that has a mean that is 37,650. And so the question is, how likely is it that we could have gotten such a result due to chance, provided the manufacturer's claim is correct? So we're going to calculate the probability. So z-score first. So we're comparing our sample mean against the mean of the sample means. We'll have to remember to adjust the standard deviation. So our sample mean was 37,650. We're comparing that against the 38,000 claimed by the manufacturer. Our standard deviation was 1,000 miles. And then the size of our sample was 50. It was 50 brake pads. So let's calculate our z-score. So that's negative 2.47. So then the probability of our z being less than negative 2.47, using our standard normal table, that's 0.0068. So the probability, if the manufacturer's claim is correct, the probability of us getting a sample as we did is about 0.0068. That is less than a 1% chance. So based on this, I would think the manufacturer's claim is probably not true. We can't argue with our data. The data of the sample we got is what it is. And we'll talk about this more later, but basically, if we end up getting a sample that is really unlikely, as we have, then basically something has got to give. And since we can't argue with the data, what we conclude is that the mean is probably not actually going to be 38,000. It's probably, in fact, less. For part C, we want to know if it's significant for an individual brake pad to last for 37,650 miles. So let's go ahead and calculate that. Here we're looking at an individual brake pad. So we have a single one, 37,650 miles compared to the 38,000 miles. Here our standard deviation, just 1,000. So that's negative 0.35 off of our Z table. .3632. Okay, so that's a 30% chance. To me, that doesn't seem as unlikely as 0.0068. So I don't think that's significant. It's easier for an individual to vary. That's why when we take samples to test something like this, we take samples of a number of things. That is, why do you think that this agency checked 50 brake pads? Because checking just one wouldn't have been that informative. Okay, so what this has to do with, and what we'll spend more time on, is the rare event rule for inferential statistics, which we've seen before, but is worth repeating here. It says, if under a given assumption, the probability of a particular observed event is very small, and the observed event occurs significantly less or significantly greater than what we typically expect with that assumption, then we conclude that the assumption is probably not correct. So like I said, we will talk about this more, and we will consider also more of 6.4 in our next video. Until then, have a great day.